So the idea being just that we would use a separate pointer, or depending upon what we're gonna be doing with the pointer arithmetic, we may have multiple pointers if we're need to work off of multiple locations in the array at the same time. But the idea is that we would just have additional pointers beyond the one that we used in the new statement, right? So we'd keep PTR as kind of our fixed pointer, keeping that fixed at the beginning, and then we would just use another pointer like PTR2 to actually move up and down throughout the dynamic array, or again multiple pointers if we're maybe working off of both ends of the array at the same time. So that's how we can handle things like pointer arithmetic. So here we did a statement like int star PTR2 equals PTR, meaning just take the thing that PTR is pointing at, right, and then store that in PTR2. So now we have two different pointers pointing at this same dynamic array on the heap, and then now we can safely use PTR2 to move up and down throughout the array, since we're still keeping PTR itself essentially as a fixed pointer that's pointing at the beginning of the array. So that's how we could still do things like pointer arithmetic here. And so there's a bit of a difference here in terms of when we talk about the issue of lifetime, right? So we talked about that a lot in chapter 6, but all the examples that we looked at in chapter 6 were with non-dynamic variables. So meaning we looked at regular local variables, meaning things that we're declaring within the function. And we know that our local variables either are going to go out of scope when the function ends, or possibly even before that, if we declare them within nested scope, like things like for int I equals 0, we know that variable I is going to go out of scope as soon as the for loop finishes. We also talked about static and global variables in chapter 6, and we saw that those had a longer lifetime compared to local variables, but we saw that your statics and globals would be destroyed at the end of the program, right? And in particular, when we talked about statics, we said that that was a key characteristic because that's what made it possible for a static variable to maintain its value in between function calls, right? Was the fact that when we called the function the first time and encountered that static declaration, it was going to initialize the variable the first time. But then that was only going to happen the first time we called the function, and then the values were going to continue where we left off on any future calls of the function. But we saw that your statics and globals would be destroyed at the end of the program. But all this was happening automatically, right? So it didn't really matter in terms of whether the variable was local or static. Either way, it was going to be an automatic process where it was simply going to automatically be destroyed when it goes out of scope. Now, when we're talking about dynamic data, meaning data that we're allocating with the keyword new in this case, that's not going to just happen automatically. And in fact, if we, for example, if we just simply forget to put the delete statement in, and so maybe we do a statement like what we did up here, where we said ptr equals new int and then size for the array, and then maybe we simply forget to put in the corresponding delete statement, well, that leads to a problem as well. And we'll see that that's what we sometimes call a memory leak. But the idea is we don't want to get to the end of the program and still at that point we have not removed the data from the heap that we're no longer using. So in general, right, the operating system should most likely be able to eventually catch that and correct that. But we really don't want it to come to that point, right? We really want to make sure that we're properly managing the data on the heap and really removing it as soon as we no longer need it. Because as soon as we do that, then like, let's say we're declaring a really big array. So maybe it's not just 5 integers, but maybe 100 or even 1,000. As soon as we use the delete statement, that array is then going to be removed from that area of the heap. And then we can use that area of the heap now to store something else, such as another separate dynamic array that we might need to create some point later in the program. If we don't do that and we just kind of let it sit there, well, then certainly we're not going to be able to use that area of the heap as long as that array is sitting there, even if we don't actually refer to the array anymore from that point in the program going forward. So the idea is that we can handle this by just using this delete operator as soon as we are done using the thing that we just allocated dynamically. So rather than, for example, waiting till the end of the program, we can just go ahead and do it as soon as we're done using it. And we'll see that there's 2 different syntax forms for delete as well. So we can avoid these problems. Actually, there's 2 things that we can do in general to really avoid running into problems like this with dynamic data. So it has to do with, the issues have to do with memory. And so the first problem that we can run into is what we call a memory leak. And that just means simply that we did not remove the data from the heap when we were done using it. So for example, we just simply forgot to put a delete statement in the first place. And so now we end the program with that data still being on the heap. Right now, the operating system is going to have to try and, detect that and clean that up, when we really, as the programmer, should have dealt with that in the program logic. So that problem is what we call a memory leak, right? We simply never deleted the data in the first place. The other issue that we can run into is what's called a dangling pointer. And with that problem, we did correctly delete the data. So if we allocated an entire array of values dynamically, meaning at runtime, with new, and then when we were done using the array, we did properly use the delete statement. But at the same time, we also kept that pointer, say PTR, we kept that pointer still pointing at the location on the heap where the array previously was. We call that problem a dangling pointer because as soon as that data is gone from the heap, if the pointer variable is still going to exist after deleting the data. So there was a period of time where we were actually working with the array, and certainly while that was going on, we needed to have PTR point at the beginning of that array. But then we reached the point in the program where we're done using that array altogether, and so we use the delete statement. But then there's other things that happen, and the pointer variable PTR itself, right, still exists, and we still keep it pointing at that location on the heap, even though the array itself is now gone from the heap. So we call that sometimes we call that a dangling pointer, in the sense that we're leaving the pointer kind of dangling at that location, even though the data that it was previously pointing at is now no longer there. We really don't want that kind of situation either. So we always want any sort of pointer variable that we have in our program environment, we always want to be pointing at either null PTR, because we talked before about how null PTR is a placeholder and that it represents address 0. And we said before that you can't actually do any sort of meaningful work, right, as long as it's pointing at null PTR, because we said before that, for example, if you try to dereference it, we're not going to be able to access the data there. But it was nonetheless a placeholder in the sense that we at least knew and we were controlling where it was pointing at. And then we would later change it to where instead of pointing at null PTR, it would be pointing at some actual real tangible data that we can work with, such as an integer or maybe the beginning of an array of integers. So it should always be one of those two things, though. It should be pointing at either null PTR or at actual real data that we can work with right now in the moment. So if the array has simply been removed from the heap, then we shouldn't keep the pointer there anymore. And so what you can do, and now whether you really have to do this or not depends also on how close, in terms of when you delete the data and how much longer that pointer variable is going to continue to exist. So meaning, for example, let's say we delete the data right before the end of main, for example, because it's the very last thing that happens is that we delete the array because maybe we do need that array all the way up until the end of main. Well, then it's one of those things where we'll show in a moment what you can do to avoid this problem of dangling pointer. It's kind of one of those things where you could still do it, it's not going to hurt anything, but at the same time, the pointer itself is going to be, right after that, is going to be going out of scope, meaning the pointer variable itself is going to be deleted. So, in that case, we don't necessarily have to worry so much about dangling pointer, but it's more of an issue, especially if there's going to be other things that we're doing in the program after we've deleted the data. Meaning we delete the data, but then PTR itself still exists, meaning the actual pointer variable still exists, and we don't want to leave it there for a period of time while the program is still continuing. And so what we'll see is that if you delete the data first, and we'll show the syntax for delete here, but if you delete the data first, and then right after that, you say PTR, for example, equals null pointer, well, now we've avoided both issues, both the issue of memory leak where we forgot, simply forgot to use delete to begin with. We avoided that since we did use delete. And then if right after that delete statement, if we said PTR equals null pointer, well, now we've also avoided a dangling pointer because we're saying that as soon as that data has been removed from the heap, we're immediately changing PTR to point at null pointer. And so now it no longer points at that old location on the heap where the, for example, the dynamic array previously was being stored. So if we do those two things back to back, as soon as we're done using the data, and then we automatically are going to avoid both of those two problems. So it'll be the delete statement first. And then right after that, the idea is that we would make PTR point at something else. Now that could be either null pointer, if we're not going to actually, let's say we're not going to use PTR to actually point at something else for the rest of the program, then we could just simply set it to null pointer. Or maybe we're going to have it point at something else, right? We're going to kind of repurpose the pointer and have it point at something else after we're done using the dynamic array that it was previously pointing at. So either of those is fine, depending upon whether we're going to use that pointer in some other way or not. But the main thing is that we don't want to just kind of leave it sitting there pointing at the heap even after the data has been gone. So we'll just see how to combine those two things together to avoid both problems. And so the first here is just, the syntax is just the word delete. So that's another keyword and operator. And then the name of the pointer. So the pointer that we use after delete would be the one that's pointing at the dynamic data. So meaning that if we previously used the first version of new, so like we used a statement like this or a statement like this, maybe, then the corresponding delete would be just the word delete and then PTR. And then that's going to delete that single value from the heap. So in this case, a single integer value. If, on the other hand, we created an array, right, maybe an entire array of values, then the brackets are also going to show up in the delete statement as well. And so the syntax here for the array version of delete is just delete bracket PTR with the brackets first. And so what that's going to do is it's going to make sure that the entire array, so the pointer itself, right, we know only points to one address at a time, right? In this case, the beginning address. But it's going to make sure that that entire array gets cleaned up, meaning all the elements get removed from the heap. So it is important in that sense to make sure that your delete matches up with your new. Otherwise, we get into things like undefined behavior. If we, for example, use the array version of new, but then only use this version of delete, or use new to allocate a single value, but then use this version delete. So you want to make sure that your delete always matches up with your new. But this one's going to make sure that the whole array gets cleaned up. Now, the other important thing here in terms of delete is it's also important that we make the distinction between the pointer itself, which in this case we're just kind of generically using PTR, but the pointer that comes after delete would be the one that you used with new. Um, the pointer itself, right? We have to distinguish that from the data that it's pointing at. So when we say delete PTR, we're not saying, for example, that the variable PTR is no longer going to exist, right? The pointer itself, PTR, still exists, right? It's still a valid variable that we can use after the delete statement. What we are saying, though, is that whatever PTR is pointing at, that's what we're getting rid of. That the actual data itself is what we're getting rid of. So PTR itself, right, is still going to continue to exist past the delete statement. So we're not trying to like delete the pointer variable, but rather we're wanting to delete the data that the pointer is pointing at, where that data could be either a single value or possibly an entire array of values if we set that up previously with new. So because that distinction is important. And also with these examples here, um, we also know that the pointer itself, meaning PTR, is not on the heap. So only the data that it's pointing at, meaning when we said, new int or new int array, that single value or that array of integers are on the heap, but PTR itself, meaning the pointer variable PTR itself, is not on the heap. So that's just a regular, if you want to use that term, but that's just a regular, local variable that's on the stack, just like anything else that would be created non-dynamically. So it is going to still exist after the delete statement. So the delete statement here, again, we said that you want to use it as soon as you're done using the dynamic data. And we also said that as long as you do that and follow that rule, then you're going to avoid that situation of having the data still sitting on that heap part of memory, even after you're done using it. And so that will lead us now into the two problems that you can run into and how to avoid both of them. So memory leak, again, just means that we never deleted it. So we can avoid that by just making sure to use it as soon, meaning the delete operator, as soon as we're no longer using that data. As long as we do that, then we're going to avoid that problem. And then the second problem is what we call dangling pointer. And so that's where that phrase dangling, right? We sometimes call that, again, dangling pointer. The idea being that even though at some point it actually was pointing at the real data, now that data is gone, but we just sort of left it there anyways for the rest of the program. And in that case, we're implying that, we did delete the data, so we don't have a memory leak or anything like that. But this is really still not a good situation either, because when that data is no longer there, we really shouldn't leave the pointer there. So as soon as we clean up the data itself, meaning as soon as we move the data itself from the heap, we want to point that pointer at something else right after that, and then we're going to avoid both problems. So that's a dangling pointer. But here's how we can avoid both problems. So as long as we do these kind of two statements back to back, right, we're going to automatically avoid both of these problems. So it always would be the delete statement first, because when we encounter the delete statement, we would still at that time, right, we need to have PTR pointing at the location on the heap where the data is. So in that sense, we would say delete bracket PTR first, but then right after that, the idea is we now are just going to make PTR point at something else. And so one thing that we could certainly do here, especially if we're not going to use PTR for some other purpose right after the delete statement, then we can just make it point at null PTR. And then we're going to automatically avoid those two problems, as long as we do them in this order. And now, certainly, if we tried to, do something like flip the order, that's also going to be problematic, right? Because if we tried to, for example, do the PTR equals null pointer first, well, then the problem is by the time we got to the delete statement, PTR would not be pointing at the dynamic array, but now it would be pointing at null pointer. So now it wouldn't actually be able to clean up the array itself and remove that from the heap. So that kind of thing would still go through, because if the pointer's pointing at null PTR and then we hit a delete statement with that pointer that's pointing at null PTR, that's going to essentially have no impact, right? That's not going to delete anything, but the implication is that the data would still would be left on the heap, right? So you still would end up with a memory leak. So the order in that sense does matter, right? Meaning the order of these two statements. And you'll see similar things also in the assignment. In particular, if you looked at the most recent assignment, some things were already in there for you. And so you saw an example of what it looked like to have a function that was returning a address, meaning, for example, a function that has the return type int star. And in the body of that function, you saw things like return new, int, for example, and then the size inside the brackets. And then there was a corresponding delete statement also that was used as soon as that dynamic array was no longer being used. Now, sometimes if we're doing the delete statement, let's say, right before the pointer itself is about to go out of scope, then we may not necessarily always do the whole PTR equals null pointer. So meaning, like, if you're in your function, and it could be another function as well, not necessarily main. but meaning if you, so let's say you're using your dynamic array. I'm gonna just omit some of the code here. But let's just say you have a function like this, and then there's a portion where you use the array, and then PTR itself, meaning the pointer, is just a regular local variable, meaning a non-dynamic, right? So the array is dynamic, but the pointer PTR itself is just a regular local variable. And then you use that pointer throughout the function. But it works out to where you basically end up using that pointer throughout the entire function. In other words, you're not ready to delete the pointer until the very end of the function, which is also the time when PTR itself would go out of scope. Well, in that case, it's one of those things where it's certainly not going to hurt anything. If we say like PTR equals null pointer, but at the same time, right? Of course, when we hit the right curly bracket, we know that the local pointer variable itself, PTR, is going to be destroyed because it's going to go out of scope. So that's one of those times where we don't necessarily have to do the whole PTR equals null pointer right after the delete statement, given the fact that PTR itself is right after that is going to immediately be removed. But where it is a concern is if you have, let's say a bunch of other things happening after the delete statement. That's where we really do want to make sure that we're doing this. So that's just, a little extra detail there. Again, it's not going to hurt anything if we just kind of, as a rule, always do this statement right after, right? That's not going to hurt anything or cause any problems, but it's just one of those things where if it's the very last thing, then it's also not going to cause any problems. So in that sense, if the delete statement, meaning a statement like delete bracket PTR, if that's happening right before the pointer itself is about to be destroyed, then having the statement to null pointer is really optional in the sense that it's not going to really hurt anything or cause any problems if we don't have that. But if we're going to be doing a bunch of other things, which is certainly possible, right? It just kind of depends on what the function's doing and the duration of in terms of how long we're using the data. So maybe we're creating this dynamic array and we're using it for one specific purpose, but then after we're done using the array, the function is still going to be doing something else. And so if that's the case, then we would want to do this statement right after. So sometimes you'll see the PTR, the reassigning it to null pointer. Sometimes you won't, but that usually will come down to whether the pointer itself is going to be destroyed right after or not. But as a rule, it's certainly fine if we did want to put that right after. That's just a little bit more detail. But now taking this into functions, right? Because now we have an idea of what operator new does, what operator delete does, and how the two can be used together to facilitate this whole process of dynamic data. And again, this is something that's very powerful, because when you think about the vector class, it really comes down to things like this, right? When you think about how the pushback function really works, in the sense of I can start my vector empty, and then I can keep adding new elements with pushback, and I can keep doing that based on how big I need it to be, and I can change that on the fly. Well, but that's coming down to things like new and delete, right? So you can imagine, when thinking about things like, well, what's kind of going on behind the scenes when I call pushback, because one of the things that we talked about back in chapter 7 was that in general, there's different ways of implementing that when you think about the size versus the capacity of the vector. Because one thing that we hit on was the fact that when the size reaches the capacity, meaning your capacity currently in your vector is 10, and your size is 10, so meaning you're full, and now you want to add an 11th element, we said that there was in general different ways of potentially handling that. And one approach was that you could double the capacity. So for example, size is 10, capacity is 10, we're about to add an 11th element, but instead of simply increasing the capacity to 11, we're going to go ahead and double it to 20, right? So that way we have some leeway, in the sense that we can add more elements before we would have to make the capacity bigger yet again. But when you think about that whole process, right? So we're calling pushback, size is 10, capacity is 10, we want to add an 11th element, but we can't physically do that right now with its current size. So what are we going to do? Well, we're going to use things like operator new, right, to dynamically create the array, because we know that a vector is ultimately, the underlying structure is an array, but it's a dynamic array. So if the array, right, that the vector is based on is currently full at 10, and now we're going to double the capacity to 20, and so that's going to involve operator new, right? Physically redeclaring it with operator new of size 20. So now there's going to be that brief window where on the one hand, you have the old vector, the old array of size 10 that has your first 10 elements. And now you just created this new larger vector of size 20 somewhere else, right? And that's the key thing, is that we know that whenever you are declaring an array, since all the elements, however big it is, they all have to be stored back to back, that when we declare it, we have to find a block, or really the operating system has to find a block of memory that is physically big enough to fit the whole thing in one go, in one continuous block. So in this case, we would have the new array that the vector is based on of size 20. So we used operator new to do that, right? New, for example, int with 20 in this case, create that dynamically as a new array of size 20. Now we could go through and from the old array that the vector was previously based on, right, copy those 10 elements from the old array to the new array, and then go ahead and add that new 11th element now into, for example, index number 10 in the new array, which is size 20. And since we doubled it in this case, now if we want to add a 12th element, right, or a 13th element, well, that's not going to involve us, at least not yet, it's not going to involve us having to recreate the array of a bigger size, right? Because when we want to add the 12th element, since we made the size 20, well, we have that flexibility. Now we can just add the 12th element, add the 13th element, and so on. But it's involving things like new and delete, right? Because you can imagine we had to use operator new, create the new array of size 20, have some sort of loop, copy the elements from the old array to the new array. And then once that's done, certainly we would want to go and we would want to delete the old array of that smaller size of 10, right? Because we don't want to, have the new array that's the larger size and then still have the old array of the smaller size on there at the same time, right? Because we don't at that point need the smaller array. So once we've copied the elements from the small array to the new array, well, now we can just simply delete the older array. And then now the new array is going to be the basis of the vector, and that old array is going to be gone. So it's using these exact ideas, right? It's using things like new and delete to manage that entire vector. So whenever we think about inserting new elements or removing elements, right, we also want to keep in mind that that's what's really going on, is using dynamic arrays, which are ultimately being managed with things like the new operator and the delete operator. So that's the basis of the vector class. And so what we're doing now is we're just getting a little bit of an idea in terms of how you would do this yourself, right, by manually using new and delete. And in terms of functions, this is also a case where we might want to actually have a pointer as the return type. So in the examples from last time, we started looking at functions in terms of input parameters. And we looked at the things like the different combinations in terms of const versus non-const, meaning the pointer, for example, is constant or maybe not constant, or the data is constant or not constant. We looked at all those different combinations. But with dynamic memory allocation, this would be a time where it might actually make sense to have a pointer as the return type, because we might want to have a special function that actually creates the dynamic data, meaning this function itself would be where we use operator new, and then that would be connecting up with another pointer, which is actually what you'll see in your assignment from last week. Is one of the functions is going to have that return type of int star, and then that function itself is where the new statement takes place. So just as we can have functions as input parameters, and we saw that that if you did that, then you could use that to do things like print out, using, for example, pointer notation, print out all the elements of the array. Or if it was just a single value that you were passing to your pointer parameter, then you could use pointer notation to point out that single value. But in terms of having it on the other side of the function, meaning as the return value rather than just the input value, a case where that really comes up is dynamic memory allocation, where the function itself is going to be where you use operator new. And so we can do things like have maybe an integer parameter with the size. So we could pass in any value in terms of the size, and then the function itself is going to use operator new and that size to dynamically create, for example, an array of integers of that size. And then in terms of what it's returning or what it's sending back, that would be the memory address of where that array starts. So in that sense, if we're going to have a function like that, then since the function is returning, and the return type would be something like int star, assuming we want to dynamically allocate maybe an array of integers, then the function call itself is going to look like an assignment statement, right? Where you'd have the name of the pointer on the left of the assignment or the equal, and then on the right-hand side would be the function call, which is returning the memory address. So that's another thing that we'll see as well as we start getting into code examples of this, is that we can also do dynamic memory allocation in terms of a separate function as well. And again, you're going to see this function something like similar to this in your assignment. But so here, in this case, there's no pointer input parameter, but there is a pointer syntax in terms of the return type. So return type is int star. And what we could do here in the body, can actually do this really with just one line if we want, but return, for example, new int size. Or if you wanted to, you could do a little bit, you could, for example, declare a local pointer PTR within the function and then do something like for example, int star PTR equals new int size, return PTR. But since we're doing this locally within the function, and this function really just has one purpose, which is to take in a size as an integer value and then declare an array of integers of that size, and that's it, right? So that's the one purpose of this function. So in that sense, we don't necessarily have to go through the whole process of creating a local pointer PTR, making PTR equals new int size, and then return PTR. That would also work, but since the goal of this function is just to simply create the data itself and then return the address, all we really have to do is a statement like this. Because the idea is that even if we did, let's say we did create, we'll just show the alternative way here, but let's say we did do something maybe like this. For example, int star PTR equals null pointer, PTR equals new int size, and then return PTR. If we did something like that, that would have the same end result in the sense that it would be correct also. But PTR itself, the pointer, is going to be destroyed as soon as you leave this function. So there's not really any benefit to doing that. So with a function like this, where we're wanting to just dynamically create an array with whatever size is passed in, the idea is that we can really just do the one line here that says return statement, the new int size. Because the whole idea is that we need to connect with what's happening here with our corresponding function call back in main. So as long as we're assuming that main is going to be the function that calls this function, then we just need to make sure that back in main that we have a pointer storing the value that's returned from the make array call. And then it would be that pointer that we actually use, for example, back in main to process this whole array. So in that sense, the make array function itself is not actually doing any work in terms of processing the array. All we're strictly doing with make array is creating the array itself, right, for the first time on the heap, and then we're returning it. But the actual work in terms of using this array to do something, such as printing out all the values, or maybe building the array with user input or things like that, that would be taking place in main and possibly other functions as well, right? Assuming that main might, for example, call other functions to print out the array contents and so on and so forth. So make array itself is just strictly creating the array and that's it. So that's why it's okay that there's, even though there's no pointer variable with this one line implementation. That's fine as long as we're connecting that up with one of the pointers back in main. So now when we think about the function call, meaning when we call this function in main, it's going to be an assignment statement where we're going to have a pointer on the left and then the name of the make array function on the right. And just a brief example here, at least in the Word document. But we could just get in again, since this is going to be a dynamic array, the size could be potentially coming from user input. So it does not have to be a constant or a fixed size like we were doing previously. So we could, for example, let the user choose that, and then the function call could just be something like this. So meaning an assignment statement where, but what you would have on the left would be the pointer that you want to use to work with the dynamic array. So that's how we can do this in terms of a function, right? So instead of course, we looked above at some examples of how you could do within the same function, like ptr equals new int size, right? If you're assuming you're declaring it within the same function, but this is also now giving us an idea in terms of how you would do it if it's going to be a separate function that actually physically creates the array. And regardless of how we, because we mentioned here that there's technically a few different ways that you could actually implement a function like make array. We said that one way would be to create a local pointer variable within make array, and then do things like ptr equals new int size, return ptr. But regardless of how you actually implement make array, because even if we do, create a local pointer ptr make array, that pointer itself is going to go out of scope when make array ends. So in that sense, in the function that calls make array, you're still going to need a pointer to store the address that make array returns to actually be able to work with that dynamic data. Meaning that, if we just did something like, let's say we did something like this. So make array size, but that's all that we do in terms of the function call. That is possible, right, in the sense that that would still run and compile, but then we don't have a pointer actually pointing at the array, right? So when we're going to call a function like this that's returning a memory address, just in the same sense in a general, whenever you're calling a function that is not void, right, we almost always will have it in terms of an assignment statement, right? Just like we saw back in chapter 6, when you call a function like a sum function that's maybe returning an integer, you would almost always, right, want to set that up as an assignment statement. So that way the value that's being returned is stored somewhere so we can use that later, right, within the program. Well, it's the same exact idea with a function that's returning a pointer or an address. We definitely would want to store that somewhere, because as long as we set it up like this, well, now we can use PTR to process the array in any way as we normally would, meaning we can, for example, use pointer offset notation to print out all the elements of the array, or start changing elements in the array, or if we wanted to use pointer arithmetic, like we said before, that would also be fine, as long as but you'd have to have a separate pointer beyond PTR for that. And we'll look at the memory diagram here in a bit, because it is important to take into account also that major distinction between working with a dynamic array, which doesn't have a name directly associated with it, versus working with a regular array, if you want to call it that, or a non-dynamic array, where there is that direct array name associated with it. But we can now, using PTR, meaning this PTR here, right, process the array in any way that we normally would, depending upon what we want to do. And again, this would just be an example of what we would never want to do. But the way we can think about this is just relating it to any other type of function that returns a value. So in general, when we're calling a function that returns an actual value, meaning does not have return type void, almost always we're going to do that in terms of an assignment statement. So this here is perfectly fine. This here still would create the array of the right size, but then we have no way to actually use it, right? So it's and then that also leads to things like memory leaks, right? Because if we don't have a pointer to it, we can't use it, and then we also can't delete it when we're done using it. So it's multiple problems really in that sense. But up here is what we're doing is perfectly fine. And so now we can process the array using PTR, and then just like we mentioned before with the delete statement, as soon as we're done using the array, that's the time where we want to use the delete statement. So we would still be doing things like the delete bracket PTR first, and then PTR equals null pointer. Those two things back to back. Especially if, again, like we said before, if the pointer is still going to exist for a while after you've removed the data from the heap. So that would still be the whole delete bracket PTR, and then PTR equals null pointer. Right? Those two things as a pair. So, and in this case, the new and the delete are not in the same function. So previously we were looking at situations where everything was happening inside the same function, which won't necessarily always be the case, right? It is possible that the new statement will be in one function and the corresponding delete will be another function, and that's perfectly fine, right? They don't necessarily have to be in the same function, right? And going back to the different ways that we talked about implementing make array, well, certainly the delete statement, right, is not going to be in make array, right? Because the whole point of make array is to dynamically create the new array and then return the address of where it starts, right? So, certainly we're not going to go in and do something like delete bracket PTR, or delete bracket PTR right before the return statement, because that'd be deleting the thing that we just created. So in general, the new and delete will not necessarily be in the same function. And that's perfectly fine, right? Because what it all comes down to is correctly managing things with pointers, right? That's really the entire idea in terms of how we make this, this whole concept of dynamic memory allocation work, is everything, right? Everything revolves around pointers and using them in the correct way. So it's perfectly fine to have the new statement here and do this whole function with just one line of code, right? Return new in size, because what's happening here is directly linking up with what we're doing in main and it starts with this function call where, so we know that, this is creating the array of integers on the heap, and we'll look at a memory diagram here in a minute to kind of put all this together visually. But we know that that's returning the array or the starting address, which PTR points at. And then from there, we can process the array using PTR, right? Things like, for example, star PTR plus I equals to change, right, a location within the dynamic array, and so forth. And then delete is going to, even though new is in a different function, when we encounter the delete statement here, that's still going to be able to correctly remove that entire array from the heap and make sure that all those integers are going to be removed. And then right after that, we can say PTR equals null pointer, right? Especially again, if let's just assume in this example that the program is still going to continue. So maybe there's several other things that we do after the array itself is no longer being used, which is why we would also want to set PTR to null pointer. So the things that we said before, right, those still apply in the same way, regardless of whether we're if we're doing the new in main, for example, in main itself, or whether we're calling another function that does the dynamic allocation, right? Either way, everything that we said about delete and the pair of these two statements, meaning the delete first and the reassignment to null pointer after, all that still applies, right? Whether we're doing new in main itself or whether we're calling another function. So we still want to do those two statements back to back in that order, where we always delete first and then reassign PTR to point at null pointer after the dynamic data has now been removed from the heap. And last thing we'll look at here is the idea of a memory diagram. And we can just look at it in terms of this example here. So this short little program where we started by creating the size, and then we created this pointer PTR, and then we did the dynamic allocation with the call to make array. Okay, and so here we'll have, this will be the first thing we'll just say is the size variable. It's coming from main. And then we have PTR, which we know is somewhere else in memory. And in the beginning, we made PTR point at null pointer because we hadn't encountered the function call yet. So going back to our discussion on null pointer, this might be one of those times where we actually would want to do that, right? Because if we're going to declare all of our variables at the top, right, as we normally do, but we're going to be getting, you know, for example, the user is going to be determining the size. Well, then we don't know at the very beginning. We aren't really ready to call make array at the very beginning, right? Because we haven't yet got the size. So we could start by initializing to null pointer and then, you know, change that with the help of the make array function. So in the very beginning, our memory situation is just going to be like that, right? So address 0, and then this is the pointer PTR from main. And this, so this would be the initial state, right? But then we can look at, we'll look at a few different states here. So this would be the very beginning. This is before actually dynamically allocating any data. So this is just the beginning of main, essentially, where we have size, which is going to be, well, we'll assume this is after the user input. So size is 5, and then address is still going to be 0 prior to the call to make array. So this prior to the call to make array. And actually, we'll look at, just to kind of demonstrate the point, we'll look at, we'll assume that make array has been implemented with these 3 lines instead of just this line. So that way we can look at this other pointer variable as well. Because what we're going to see is that if we do it that way, then we're just going to have, for a short period of time, there's going to be the 2 separate pointers that both exist, meaning the pointer PTR from main and then the pointer PTR from make array, right? If we did implement it with the extra local variable inside of make array, just to see how that's different from the pointer back in main, right? So this would be the one snapshot, right, of memory. And then just so we can see the 2 pointers together in memory. But normally, right, the ideal way to implement make array would be to not use the local pointer. But if we do that, then there's going to be that brief window, right, where they both exist, meaning both pointers. And so we initially, in the very beginning of make array, we set it to null pointer, so address 0. But then before the function ends, of course, we hit the new statement, and then we make PTR point at that. So this would be at the very beginning of make array before the DMA has, or the dynamic memory allocation has actually taken place. So this would be before the array has been created. So there's going to be a brief window, right, in time where this would be what our memory diagram looks like. And so if we did implement, and again, it's not really ideal to do it this way, but the point is that if we did implement it with these 3 lines, as opposed to just doing this 1 line implementation, then we are going to have the 2 pointers in memory at the same time. And this is also showing us why, right, that extra pointer is not real inside of make array is not really necessary, because it's completely unrelated to the pointer from main. But this is what you would look like in the beginning of make array, and then the next thing would be, you know, after the new statement. So the new statement itself, we know that it's really doing 2 key things. So meaning when we get to this line here, we know that number 1, it's physically creating the array of integers of that size. And here in this case, they're not initialized, so just garbage values. But at the same time, it's returning the address of where that array starts. So now our memory diagram is going to get bigger, because now we're going to have the actual array of integers on there as well. So this would be the and then we'll say that this is but before we've returned back to main. So meaning that main's pointer is not going to be updated just quite yet. But if we're looking at this next state in memory, and this is also now where we, for the first time, have data on the heap, right? So remember, all these variables here that we have so far, the 2 pointers and the integer size, those are on the stack, right? Those themselves are not on the heap. So even the pointer that points at the dynamic data itself is not, in this case, on the heap. But now we're about to add in that array. Let's say that it starts at, let's say address 100 here. But this would be on like the heap. And again, at least in the beginning, garbage value. But unlike all the memory diagrams that we did in, and we'll just say that it's 5 values in the array. But the key difference also here is, unlike our diagrams that we did in chapter 7, because in chapter 7, whenever we had an array, we would always say things like, okay, ARR is the name of the array, and it refers to the starting address. But now there is nothing comparable to ARR, right? There is no array name. So everything that we do, right, is going to have to be through the pointers. And so they each take up 4 bytes here. But this would be, and again, this is on the heap, but this would be where the array itself is. We're just saying that in this example that it starts at address 120. There is no array name, right? That's the critical distinction here, how this is different from the way we thought about this in chapter 7, right? Very important distinction, but so this is the array itself, which in the beginning, it's fine if we have garbage values. We can later change that back, for example, in main or in other functions. But now the idea is that if we're looking at this snapshot in time, so this is basically towards the end of make array, but before we return back to main and update PTR in main, well then what it's going to look like there is now the local pointer PTR in make array is going to be storing the starting address of this dynamic array. So now it's going to be address 100 instead of address 0 or null PTR, right? Because it's now pointing at that dynamic array. Now, the next one we'll look at is when we've actually returned back to main, right? So meaning after we have, so after this call has finished and we actually have stored the address in PTR back in main. So at that point in time, first of all, this local PTR for make array is going to be gone from our memory diagram, right? That's completely gone. It's out of memory because it goes out of scope as soon as the make array. But it is going to be returning the address, right, of where the array starts, and that's going to be now stored in the pointer PTR from main. So now if we look at that next state, but this would be after returning, but before deleting the array. So the array is still going to be there. Then we're going to have this. And so this is now going to be out of there, right? That local pointer from make array is now gone. So in general, right, we could eventually have, something else stored at that old location, right, address 44. But so that's now the pointer PTR in main stores the starting address of the dynamic array, right? That was coming from the assignment statement, meaning this assignment statement, right? And so now we're able to process everything with that pointer PTR. But this also gives you an idea of why we were saying earlier, why if the only pointer that we're working off of is PTR, why we don't want to use pointer arithmetic over PTR. Because since there is no array name, so we need to be careful in the sense of always having at least one pointer pointing at the beginning of that dynamic array. So in other words, we really want to keep PTR here fixed at address 100. So we can either do the offset notation, or we could use a separate pointer if we really, for whatever reason, want or need to use, pointer arithmetic. But that's the idea, right? So now because we have this situation, or down here, we have this situation in memory, now we can use PTR to process the array. And at the moment, that would be the only way to process the array because that's the only pointer that has any sort of connection to the array of integers itself that's dynamically optimally heaped. And then from there, right, we could think about the next couple of states of this memory diagram because, we do eventually hit those two statements back to back, the delete statement and PTR. So we'll look at that when we continue this next time. But the idea is after the delete statement, the array is going to be gone from memory. And then PTR equals null pointer is just going to set that back to address 0 or back to null pointer to clean everything up. But that gives you an idea of, visually how we can think about this and how we're going to use that pointer to work with that array. And also the key difference in the sense that since there is no array name, that everything that we're doing is going to have to be in terms of the pointer, right? So that's why pointers play such a critical role when we're doing dynamic memory allocation. Okay, so we'll continue this next time and look at some, now that we've looked at the underlying concepts, we'll put this together with some code examples, and then we'll start looking at structures.